All right, welcome everyone. This is San Diego Machine Learning Meetup Group. So today we'll be talking about the graph neural network stuff that we've been working on for the past few sessions. So this time we'll be looking kind of more at the architecture design of the stuff that's inside of the graph neural networks that we've been talking about for a few weeks. So as is normal, if you ever have any questions, put them in the chat and I'll see those. And then if you have something that you think I'm missing, you can feel free to just ask aloud if you're able to. So feel free to interrupt and I'll answer any questions potentially. So just a small recap. We've been looking at these graph convolutions. And so you have some sort of graph and you pass it to graph convolutions and it looks at the relationships between the various nodes. And then you have something like an activation function. So you can represent nonlinear relationships. And then you might have something in here that does regularization or dropout or something like that. And then you might pass it to more graph convolutions. And then eventually you have some form of output. And that could be node embeddings, that could be a direct prediction, that could be an embedding for a graph. There's a bunch of different things that you can do with that. But we'll talk about those more in later slides. So one of the key concepts that we've been looking at is that you have some node that you're interested in. So the example that I've had in my mind throughout this whole series has been like, imagine you're trying to predict a house price and there's some relationship between all of the houses that are next to it or some other entities. So for example, you have like, let's say this is your house and then these are all of your neighbors. Obviously the price of your neighbors and the number of rooms that they have and the square footage and all kinds of other stuff that can have a bearing on what your house price might be, because if you have expensive houses near you, that probably means that your house is also expensive or cheap or vice versa. And so one of the things that we've been looking at is kind of this degrees of connectedness. So you have your house and then you might have other houses that are on your street, and then you might have other houses that are close to those other houses. And so you can go more degrees of separation away from there. And so in the end, we want to kind of propagate the information from all of the nearby nodes to tell you about that given node, just as an example of something you might want to do. Let's say we have a simple graph like this and we're interested in node A. You want to aggregate the information from all of the connecting nodes. So for example, in this one, target node is A, and we're connected to B, we're connected to C, we're connected to D. And then we want to look at the information from those ones. But then we can go even one hop further and we can say, okay, what is B connected to? B is connected to A, it's connected to C. And so the gist of this is we need to figure out, how do we connect this flow of information and how do we encode it? That's kind of what we'll be looking at today. So this is a deeper look, and it's saying, well, actually we have a different, for each node, we have a different connected graph. So if we're looking at A, we have all of its connected nodes, and then we have all of those nodes connections. And we can see all of the relationships for all of the nodes inside of this graph. And so you can see that depending on which node you're looking at, you can have a whole bunch of different connectivity. So one of the things that we're learning about in this chapter is that graph neural networks are really kind of just a general case of all of these other networks that we talk about in machine learning. So if you're looking at convolutional neural networks or transformers or pretty much anything else, it's kind of just a special case of a graph neural network. One of the special things inside of graph neural networks, though, is that you expect permutation, invariance, and equivariance. So if you have some, like let's say you're looking at your friends, for example, and those are your connected nodes, it doesn't really matter what order you input them. You can have them in any order, and you want to have it represented exactly the same. So that's one of the kind of core properties of graph neural networks, is you have this sort of set that the order doesn't matter.
What's equivariance? Sorry.
it's the same regardless of orientation in a sense. So like, for example, maybe I can explain it in terms of the convolution. So in a convolution, you might look at one pixel and you're looking at all of the pixels around it. In a convolution, in a convolutional neural network, this order actually matters. So it matters that this top left pixel is in that spot. Whereas in a graph neural network, you actually don't care. This pixel could be over there. This pixel could be over there. It doesn't really matter. It should yield the same output is what the equivariance is saying. Does that answer that question, hopefully?
Thank you.
Yeah. So thinking of this convolutional neural network as a special case of a graph neural network, we were looking at the graph neural network. It's showing like, here's the connectedness of all of the different houses around it. You can think of it in terms of like an image. So in an image, we have one pixel that would be our target node. And then the stuff that we're looking at, that we would call connected, is all of the pixels that are around it as well as itself. So if we look at this, we have this one target node that's this pixel, and then we have all of the pixels around it. And so our graph would look like this. And our graph is always going to look like that. And then we're going to just slide that window across and apply it to every target node within the image. So we apply it here in the top left, and then we'd slide it over one here, and then we would move all of the connected graph over here. And so you apply that multiple different times. So this is the whole point here is, if you're familiar with convolutional neural networks, they're actually just a special case of graph neural networks where you just assume that the connectivity is always that same 3x3 filter or whatever you're using. So then another special case in a lot of architectures lately, people have been using transformers, specifically with text. And so the example here is showing that actually transformers are just another special case of graph neural networks. So graph neural networks are kind of this very general concept of just the connectivity and the relationship of information. And then transformers and CNNs are just special constrained versions of that. And so they're showing on this slide that transformers is just fully connected relationships between all of the words. So you have the sentence, I am a Stanford student, and you're looking at the relationship between I and am, I and a, I and Stanford, I and student, and so on. So you're actually looking at all of the relationships between am as well. So this graph is fully connecting all of these words. So if you look at this, the graph might look like this, where I is connected to all of these, am is connected to all of these, etc. So there's a question, are there useful math structures where child nodes are not equivariant? Ancestry tree would be one. Each child except for twins are ordered by age. I'm not familiar enough to know if there's some special case where that would be the case. I was kind of, when I was looking through the slides and watching some lectures, I was kind of thinking that right now we want our input to be order invariant, so it doesn't matter what order you put things in. But in theory, you could do something where you have like your first element is the oldest kid, and then the next one is the next oldest kid, and then so on. But I think one of the complications with that, when you want some sort of ordering, is you can have variable amounts there. So you have to do some sort of aggregation that eventually crushes that down anyways. So if you have 5 kids versus 3 kids, you're going to have different number of outputs. And so that kind of makes things complicated. So you probably eventually want to get some summary of all of their relationships at some point. And we'll talk more about some of that aggregation stuff on later slides. So that was those various neural networks. They're all kind of special cases of graph neural networks. And then now we'll look more at some of the specifics of how people lay out graph neural networks to do well with this sort of data. So we looked at the previous slides. You have a target node, and then you're looking at all of the stuff related to it. And the two key concepts that we're going to pull out is that you're passing messages and then you're aggregating them. And so we do that as two separate steps. So if you look at this visualization down here, these would be our input features. So any colored circle is our input features. So for example, in my house price example I was talking about, this little circle would include something like the square footage, the number of bedrooms, the number of bathrooms, and various other things like that. So you can have a whole bunch of features there. And then what you want to do is you want to send a message to like up to the chain. And so this can be any number of features, but then you want to turn it into a message in some way. So you can take this and apply a linear layer to it or some other neural network operation on top of it. And then you're encoding that to a message, and then you're passing it up the chain, basically. And then at the same time, so looking at this graphic, these rectangles are the part where you're encoding this feature into the message. And then after that, you're passing the message to some aggregation function. And so for this one, the aggregation function is basically doing nothing because you're only passing it one message. But in this scenario, you actually have it sent 4 messages and then you're aggregating it in some way. And we'll talk more about what you might use for aggregations there. So this is basically, you've got some features, you encode it in some way, and then you pass it to an aggregation function. And then now this output is new features to the next layer. So this is saying, let's look at the stuff that is 2 hops away from the thing that we're interested in. And then after that, we encode all of this information. And now we're looking at 1 hop away from the thing that we're interested in. And then we do the same process of encoding this to some message from each of the input nodes. And then we're doing some aggregation. And then finally, we get our output embedding for this certain node A. So later we'll look at the various different ways that you can connect these. So this is kind of the simplest case where we just say, let's just go from all of the ones that are 2 hops away and then 1 hop away and then to the node that we're actually interested in. But we'll look at skip connections on a later slide that is a little bit more complicated design pattern. So we won't really look at it in this chapter, but there is a concept of graph feature augmentation and graph structure augmentation. That's probably something we'll talk about at a later day. So we won't touch on it today, but your exact computation graph doesn't have to be exactly what you use. So your input graph doesn't have to be your computation graph is basically what this slide is saying. So then the question is also, how do we actually train these? So we've looked at various different methods. You can do it supervised, you can do it unsupervised, you can look at the node level, you can look at the edge level, you can look at the graph level. There's all kinds of different things that you can do, but we'll discuss those a different day. So we've looked at some of the precursors to that stuff, but we'll look at this stuff in more detail in later chapters. So then now we'll just look at the individual graph neural network layers. So we've already looked at this slide a few times, so I'll just jump into the next ones and see the specific examples of what these actually look like. So we've already discussed there's sort of a 2-step process. You encode something as a message, and then you do some aggregation of all of the messages. So this is kind of the simple case. We have 3 input nodes, and then we encode those to a message, and then we do some aggregation, and then that goes to our target node V. And another important thing to note here is we probably also want to look at this node V when we're doing anything downstream. So this would be your neighbors' houses potentially and their prices. And then this might be your own house saying how many rooms, how many bathrooms, et cetera, because we also want to encode that as well. So if you look over here, you can see that we have all of these nodes are actually going into the GNN layer because we're interested in all of them. If we didn't have this added on, then we would only be looking at our neighbors when actually we also have some information about that node specifically. We might be trying to fill in something for that node or look at relationships of that node or other things like that. So now we can actually look at the specifics of what I mean when I say that we're encoding a message. So for the most part, the simplest case is you can just apply a linear layer. So you apply some linear transformation, you have some input features, and then you apply a dense network. So if you're familiar with multi-layer perceptron or any other neural network, you can kind of apply that there. So the encoding can be whatever you define. Typically, people just use a dense neural network or something like that. So you have your input features, you encode it in some way with some neural network function, typically just a linear or dense layer. And so, for example, looking at the math here, this h of u is the actual feature, and then you're applying some W weight matrix to it. And so that's what becomes these messages. So you have your input features, you apply some neural network, and then that encodes it to be this message. So it's some new vector that you're passing along.
Sorry, stupid question. In the previous slide, just very quickly, quick question.
Mm-hmm.
In that top equation there, stupid question. Yeah, on the left side they use M, notation M of U, M for message. On the left side they use H. H is, what is H?
So the H is the features. So those are the I don't know if H specifically stands for anything, but H would be these colored circles. These represent the features. So for example, this is like what I was saying, where you might have number of rooms, you might have square footage, etc. So all of this goes into some message encoding function, and it does some transformation on these features, and then it becomes this M of U. So they showed the example here. You have your features, you apply some weight matrix to them, and then that's what you get there. But this message function can be whatever, and these are the actual features that represent these nodes here.
Thank you.
Yeah. Any other questions? So then moving on and looking at the aggregations, so these are the two parts that we're looking at that actually kind of impact the architecture. So we have the message part, we have the aggregation part, and the aggregation part, we have a bunch of different options here. So what we're looking at now is we have these three messages that we've received, and we want to aggregate them in some way. And we want it to be equivariant, like we discussed earlier. So you want something where the order doesn't matter. If the blue node was in the middle instead of the green node, we don't want that to give a different result, because ultimately the layout of this doesn't actually matter. You can't put an ordering to the relationship between A and D and A and C and A and B. It doesn't matter. You could try to put some ordering there, but realistically, you probably don't want one, because it makes your network much more general if you don't have that. So looking at some of the simple options that we can use here, we could just take the sum. So you get some encoded message from 3 of these different nodes, and you just say, okay, add them all up. And then you have a new vector that is the same size as these messages. It's just been summed between the 3 of them. And so there's pros and cons to all of these different approaches. One of the issues with summing is that if you have a lot of messages coming in versus only a few, that can actually change your result. So if you have 20 messages coming in, then kind of just by default, your output is going to be 20 higher than one that only gets one message. And that may or may not be what you want. So you just have to kind of understand what the pros and cons are of that. Another option is you can just take the average. So you take the 3 of these and then you say, add them all up and then divide by 3. So then it makes it so it's invariant to the number of input messages that you have. So if you have 20 nodes versus 1 node, it's going to get something of roughly the same magnitude because it's been scaled by the number of input nodes. Another option is you can take the max. So if this is some vector, let's say it's 50 units long, you can take the max across all of those 50 units and then just take the max from each of those 50. So you still return 50, but you're taking the max across those 3. So there's a few different options there. There's fancier stuff you can do too, but generally those seem to be good enough. So one of the issues with doing this aggregation, though, is you can end up losing information over time. And you also have this issue where things aren't really treated how we want. So for example, on the previous slide, we had these 3 nodes coming in. We have the blue, the green, and the red, and those are actually our input nodes. Those are coming from somewhere else. And then we also have our target node, the yellow one. And we probably want this to be treated actually somewhat differently, because if we just summed all 4 of these, then we don't actually know which one is the target node. And so we're losing some information. And so the way some people solve this is they say, okay, we'll handle all of these messages in some way, and then we'll do a separate transformation that we've learned on the target node, just so we can at least denote this is the target node. It's slightly different than all of the related nodes, because if you were looking at all of your neighbors' houses, you probably want to be able to tell that you're looking at the neighbors' houses versus your own house, because that's probably more pertinent information. And so one way that you can do that is you can do the aggregations of your neighbors first, and then you can concatenate it with the target node. And so that makes it so you have one vector that represents the aggregation of all of your neighbors, and then you have another vector that represents the target node, and then you just concatenate them together. So you end up with something that's twice as wide, but you end up with a richer understanding of these are your neighbors and this is yourself, because you probably don't want this being counted and just aggregated and smoothed out with everything else.
Quick question on that concatenation. You mentioned that's quote, it's just vector concatenation, or meaning you just add another. So does that mean at each layer, at level, it gets bigger and bigger and bigger, or?
It depends on exactly your the layers that you define. So you can so let's say that you're at layer 2. You're 2 hops away from the target node. You have one set of layers, and let's say that encodes it at a length 50 vector. That will do 50 vector for all of your neighbors, and then it will do a 50 vector for the target node itself, or at least one hop up. So then you'll end up with 100 with a 100 length vector but then you're passing that through another linear layer, and that linear layer can map to whatever you want. So it can go from 100 back down to 50. It can go from 100 and stay at 100, et cetera. So in theory, you could have it be the same size all the way throughout and just keep doubling, doubling, doubling. But in reality, most people probably do it where it's condensing that information back down with a linear layer. So it might go from 100 back down to 50 with a linear layer.
Got it. Thank you.
Yeah. So we have our various parts. We have our message encoding. We have our aggregation. We learned the various pieces of making a message. And then we also learned the different methods for aggregation. And then another piece that we add on top of this is some form of nonlinearity. So if you're familiar with other neural network stuff, you've probably seen Relu, sigmoid. There's various different activation functions. And so we would add these at the end after the aggregation to give us some sort of nonlinearity, because if we didn't have this, then all of our steps through the network would only be able to represent linear relationships, and it's better if we have some nonlinearity in there. Are variance or uncertainty from neighbors considered during aggregation? Not that I know of. I'm sure that there's some special case of that where someone has tried something with that, but I'm not deep enough in it to necessarily know. In this flavor of it, no, I don't think so. We'll learn on a later slide about attention, and so that might be kind of pointing at what you're asking about. So the first general architecture we'll look at is just kind of generically called graph convolutional networks. And so this is kind of what we've been building all the way up to. So you have some message, and then you some messages, and then you aggregate them. And so this is kind of just the mathematical formula saying that we take the input features, we multiply them by some weight matrix, and then we divide them by the number of neighbors. And so this is kind of just a math form of what we've been looking at. Is you have a whole bunch of different input nodes. So you have the blue, the green, the red. You multiply each of those by the same weight matrix, and that transforms them into a message. And then our aggregation function is basically just the sum of all of these. And in this case, we're dividing it by the number of input nodes. So we have 1, 2, 3 here. So we're dividing each of these by 3 and then summing them up. So if we got rid of this, we would just be directly summing it. But because we're doing this additional scaling step, we're actually taking the mean. And then at the end of it, we're doing some nonlinearity. So that can be Relu, that can be any number of different things. Kind of just covered all of this. This is just showing the written out version. So this is encoding an individual message. So we have our input. So let's say this is the blue input node. We multiply it by the weight matrix, and then we multiply by 1 over the number of target nodes. And then after that, we do the summation over all of these, and then we apply the nonlinearity. This is just further broken out. So just to say, this is the graph convolutional neural network setup. And this is a common architecture that people use. And then on this next slide, we'll be looking at GraphSage, which is a different variant. So in this one, if you look back at the previous one, actually, we were doing this for all of the target nodes, and then summing them up. But in this one, we'll actually be doing what we discussed on a previous one, where we're encoding all of the input features from the previous node. We're doing that whole message and aggregation process on all of these, on all of the input nodes. And then we're also doing that on the target node, and we're concatenating these together. So for example, we have our red, green, blue dots. We're applying the message function onto all of them, and then we're aggregating. And then in my example before, like that yields some 50 length vector, and we concatenate that to the message that has been encoded by the actual target node. So this would be our yellow dot that we've been looking at. And then we can apply some weight matrix to both of these combined, and then apply some nonlinearity. So this is kind of showing that we're doing double aggregation here. We aggregate over all of the neighbors, and then we also do an aggregation along with the target node itself. So we can represent all of the neighbors. They've been summed up or mean or whatever else, and then we also concatenate that with the target node, and that gives us a deeper representation. So we actually know something about the target node. So one of the interesting things about GraphSage is it can use many different versions of aggregation all in the same network. So you can take the mean, you can take the pooling, and another. So when I say pooling can be mean, max, etc. And then another one that they mention using is an LSTM. So an LSTM can handle sequences, and typically when we think of LSTMs, we think of something time series or text or whatever else where the order actually matters. So if you go left to right, you expect a sentence to start with a certain word and then go in a certain direction. And this we can make this still work even with stuff that we don't care the order about by just doing random shuffles. So every time you do the input, you just shuffle the input, and then the LSTM can do some form of aggregation where the order actually doesn't matter, and it will learn to take into account all of the bits of information where the order doesn't matter, but it can represent it in a bit more complicated of a way than just a mean or max or something like that. So sometimes this can be useful as an aggregation function as well. Another thing that they introduce into the GraphSage algorithm is they add in the L2 norm. And so this is just something optionally you can add on various different layers. So actually normalizing the outputs of the various nodes can make it so that they're scaled more consistently, and then that can help you pass information more effectively. So the L2 norm here is just you take the square of all of the values and then you sum that up, and then you take the square root of it. And so you calculate that norm, and then you divide all of the features of the node by that, and it makes it so they're normalized to a consistent scale. So you don't end up with things that are drastically different scales. And in some cases, this is shown to improve the performance. I wouldn't really worry too much about this. This is kind of just something that is in a lot of layers slightly. So you can, if you use various different libraries, it will probably already be in there for you by default. I can pause here. Any questions? Anything I should go back to? All right.
I just wanted to know that equivalence means not only rotation, it means a shift too. And as far, well, as far as I remember, every node should be treated the same if they have the same neighbors, right? With the same properties.
Yeah.
So we could shift to another node, but it still should be the same process.
Mm-hmm.
Okay.
Yeah, exactly. So the next evolution we'll be looking at are graph attention networks. And so this is kind of an extension of both of the previous methods. So if you look at what we were doing in the previous setups, we had this weighting factor. We didn't call it that at the time, but this is basically if you're taking the mean of something, you're saying everything gets the same importance. So if you have 3 nodes, everything gets 1/3 of the weight. And that might be a useful assumption just for simplicity's sake, but in reality, we probably do actually want to weight them differently. So if you have your own house and then you have your neighbor's house, and one of them is 100 feet away from you and another one is 2 miles away from you, you probably want the closer one to factor in more. And so this attention method is something that allows you to try to make the model learn that. And so instead of just saying everything gets equal weight, all of my neighbors get the same evaluation, you can apply this additional attention layer, and it will try to actually learn which of these are relevant, which ones should be more highly weighted, and which ones should be kind of left behind, because some of them might actually not be that useful. So previously, we were assuming that all neighbors were equally important, but we know that that's probably not the case. But then we have to figure out, how do we fill in that information? How do we determine their importance? So basically, what we can do is we can also learn some attention weights that will tell us how to scale this. So before we had our summation, where we have some input features, we have a weight matrix, we multiply these together, and that's the message we want to pass. And then we want to do some aggregation. And before, we were aggregating just saying, let's take the mean of this. But in reality, what we could do is we could do an unequal mean, where the attention weights actually tell us how much attention to put on each of these different messages that we're receiving. And so we're looking at, how do we assign importance to these different messages that we're receiving, and we have to figure out some sort of some way to predict a weight for each of these different input messages that we're receiving. So the way that we can do this is we can use an attention mechanism, where basically we are looking at the various connected nodes and then we're making a prediction about their importance. So for example, if we're looking at A, we can look at the connection between A and B, A and C, A and D, and then we output some coefficient saying how important is the relationship between these. So for example, one way of doing this is you train some additional linear layer, and then you pass in the pairs of connections, and then you just have it make an output on the importance of these. So for example, you do the process I was saying. So you look at A and D, you pass these in, you concatenate them together, and then you apply some dense layer or something like that. You concatenate A and D, and then you have it make a prediction and say, how much weight should we give to A and D? How much weight should we give for A and C? How much weight should we give for A and B? And then that's a new scaling factor for how these messages are passed along. Question about the attention mechanism only looks at directly connected nodes. Yes. So on a specific node level, we're only looking at the ones that are connected. But then if you look deeper in the network, we're doing that multiple times. So we are seeing the deeper relationship. So for example, in this one, we're looking at all of the connected nodes for A at the first step, but we're also looking at C at 2 steps away. And from that one, we can potentially do some weighting for C and E and F. So these ones are also connected. If we look 2 hops back, we are actually probably doing attention on the further nodes as well. So yeah, I would say that the attention is local to your specific target node. But if you look at the process that we're doing on the graph neural networks, we're always going deeper and deeper. So we'll look at another slide in a second that will kind of explain what I'm saying better. So what I was mentioning is we take the pairwise of all of the connected nodes, so AD, AC, AB, and we get a score for each of those. And then we can apply the softmax to that. And the softmax is this function that will normalize it so they all sum up to 1. And so basically what this is doing is it's saying, let's say A and D gets a score of 3, A and C gets a score of 17, A and B gets a score of 1. Each of these gets an input score, but then we apply the softmax to it, and then it reduces it down to sort of like a percentage. So A and D might get a score of like 0.2, A and C might get a score of like 0.7, and A and B might get something like 0.1. I don't, those numbers aren't exact. I'm just kind of representing the softmax makes it so that you're giving each of them some portion of something that sums to 1. So you're saying give it 10% this, 20% that, 70% this, and it all sums up to 1. Just saying give each of these a partial weighted sum. So that's telling you what factor to weight your sum by. So like I was mentioning, let's say that A and B are your connected nodes and you want to figure out the attention weight to apply to them. One thing you can do is you can concatenate them. So you have node A is connected to node B. We concatenate them. So now we have this vector that's A and B, and then we apply it to we pass it through some linear layer, and that will give us actually our output weight. So we're directly looking at the features of this and creating some weight. So you're predicting how important that feature is. That's what attention is doing, is it's trying to focus on the stuff that is actually important. So another variant of this is multi-headed attention. So what we were just looking at is just a single head of attention. So you have that single output. So it would be the 0.1, 0.7, 0.2 that I was talking about. You can actually train multiple attention heads all at once. So let's say in this example, we do 3, and you randomly initialize 3 different attention defining networks, and you can apply those to all of them, and then you do either a concatenation or a summation or something like that. And so what this will do is you have multiple different looks at the attention. So one attention head might tell you 0.1, 0.7, 0.2. Another one might tell you 0.3, 0.3, 0.4. And so you can have multiple different looks at the same data. And in theory, this kind of stabilizes things. And you can also have multiple different views of the same thing. So downstream, you might be able to do different things with the different attention heads, and the network is able to learn that. So the nice properties about the attention mechanism, it's pretty fast to compute. It's just the same as any other dense layer. And with most of the stuff that we do with the graph neural networks, it's efficient because we are operating on sparse matrices. So like, for example, with the CNN example we were looking at before, you're assuming full connectivity, and luckily we're not doing that with our graphs. We're only looking at the stuff that is actually connected, so you can operate on them sparse, and you don't have to worry too much about the massive crush of all of the interconnections because we're only looking at the ones that actually matter and are connected. And like you guys were saying, it only attends over local network neighborhoods. So looking at the kind of overall design, we can plug in a bunch of different stuff into these graph neural networks, all of the usual deep learning stuff that we do. So you might have linear layers, you might have batch norm, you might have dropout, you can do activations, you can do attention. There's a bunch of different things that can go into a specific graph neural network layer. You can design it really however you want. The important part is just that what makes it a graph neural network is understanding how do you encode a message, how do you aggregate it, and then that's kind of what makes it unique. And then the actual internals of it can be whatever deep learning magic that you want to add in there. So like I mentioned, you can add in batch normalization. If you're familiar with that, you can do dropout, you can do attention, and you can do pretty much anything else. You can have LSTMs in there, you can have CNNs, you can have transformers, you can have all kinds of different things inside of these networks. So looking at batch normalization just briefly, I don't think it's actually too important that you know this for the sake of graph neural networks, but a trick that ends up in a lot of neural networks is batch normalization. And what this is essentially doing is it's looking at the means of the features, and then it is scaling them down. So what you do is you subtract the mean and then divide by the standard deviation, and that makes it so everything is centered around 0 and has unit variance. And this just makes it a nice property so that you don't have instability going out further through the network. I wouldn't really be too concerned with that. There's all kinds of different normalization schemes. Batch normalization is a common one. If you're interested in that, you can look it up, but I would say it's not super key to understand the graph neural networks, actually. So another one that we have is dropout. If you're familiar with deep learning stuff, you've probably seen this. Dropout is basically the concept that you turn off different neurons during training, and that kind of forces you down different paths of the neural network. So you're not entirely reliant on individual features. So for example, with the housing example again, if you have your number of rooms, number of bathrooms, square footage, etc., using dropout, you might randomly turn off some of those neurons, basically. So you say, let's not look at square footage for this specific training pass. And so what that does is it forces the network to learn other features as well. If it doesn't have the features present, then it can't learn from them, and it has to learn from the other stuff. And it kind of evens out the contribution of the other features rather than just relying exclusively on one feature or one pattern that is very predictive. Dropout kind of forces some regularization and utilization of a bunch of the different features rather than just relying on whichever ones are most predictive and then forcing down that path. So what they're saying here is that you have your linear layers throughout your neural network probably, and you want to apply dropout to the linear layers. You could apply dropout at kind of different levels, but what people have found to be successful is actually doing dropout on the features of the message. So one other variation is you might actually want dropout of messages. So for example, up here, we have these 3 messages. One variant could be, let's just randomly exclude entire messages. But in practice, what people have found is more successful is just doing dropout on the individual features. So you're still passing something from all of the messages, but it might be a sort of corrupted version of those messages. But on other versions, you could try to just turn off messages entirely. Mentioned on previous slides, there's activation functions that we throw in here. We want our relationships to be nonlinear, and so we apply these various nonlinear functions on top of them. So a common one is Relu, another one is sigmoid. There's also parametric Relu. So again, I would say this is kind of nice to know, but you don't really have to know it too deeply. The gist of Relu, though, is anything 0 or below ends up just being 0, and then anything above 0 ends up just being the input value. So if you have some neuron and it fires at 50, then it will output 50. If it outputs -1, then it actually just outputs 0 for Relu. And then sigmoid is its whole own thing. It basically constrains everything to be from 0 to 1 on the y-axis. This is still popular for your output neuron. You might want to use a sigmoid activation function, but in reality, a lot of people don't actually want these inside of their neural networks like the middle layers anymore, but they still might be used for the output layers. And then the parametric Relu, it's the same on the right side as the normal Relu, but then on the left side, we have some scaling factor. So for example, like before I said, if you pass in 50, it will output 50 on the right side. But if you pass in -10 here, you might have some scaling factor that makes it so it's only -1 on the output, for example, whereas on the rectified linear, it would just output 0 every time for anything that's negative. And so people have found that this performs better than Relu in general, because Relu actually just loses the magnitude of anything going negative, and the parametric Relu allows us to have this non-linearity, but it still passes some information through when it goes negative.
Hey, Ryan, quickly, I just wanted to ask, like, not heard of parametric Relu earlier. Can we use parametric Relu in normal, like multi-layer perceptron or even the normal convolution neural networks?
Yeah. And it's actually Relu is very common. A lot of people use that, but there's been all kinds of variants of Relu that have been found to actually give you small boosts. And that's true of almost any network. So you can use different variants of Relu. There's JLU and SALU and a bunch of different stuff. Parametric Relu is a pretty common one, but yeah, they can be applied any neural network basically, and it will probably give you a small bump over Relu. If you look at the stuff in a lot of the transformers and computer vision architectures, they won't have basic Relu anymore. They'll have something like parametric Relu.
Okay, great. Thanks.
So just in summary of this, we can plug in pretty much any deep learning module into these graph neural networks. We have lots of options here. So the nice thing about the graph neural networks is if you have knowledge of the deep learning, a lot of it will carry over. So if you have some special way that you like to handle text or images or whatever else, you can actually encode it and then pass it to a graph neural network, and your graph neural network can directly handle that stuff. So any deep learning stuff, you can integrate that as well. And so one of the resources that Stanford shared is they have this GraphGym library that's kind of designed to allow people to try new actual specific graph neural network stuff. Because right now, a ton of this stuff is just generic deep learning stuff, but maybe there's something graph neural network specific that you might be able to implement, and it can yield something that's even better than sort of the generic stuff that you can plug in here. But that's something that's still being researched. Graph neural networks have been around, but they're kind of getting hotter lately. So people are still researching these. Any questions at that point? Yeah, so parametric Relu is similar to leaky. Yeah. So I mentioned earlier, we can stack these layers in various different ways. So the simplest possible way is what we've been describing this whole time, which is saying we have these nodes that are 2 hops away, and then those get encoded to a message and then aggregated. And then we just pass all of that sequentially along. But there's more complicated variations where you can introduce skip connections. And so what these allow you to do is, actually, I'll pause on that for a second so we can talk about the oversmoothing problem for a second. So the skip connections solve this oversmoothing problem. And what this oversmoothing problem is saying basically is if we stack a whole bunch of graph neural network layers, every single time we're looking at further relationships of the graph. So if we go 1 layer deep, we're looking at all of the neighbors of our target node. If we go 2 layers deep, we're looking at all of those neighbors. And then if we go 3 layers deep, we're doing neighbors. And at that point, we're covering a whole ton of the graph, probably dependent on the interconnectedness. Like I don't remember the exact number, but people always say like you can have a relationship with anyone that's 7 degrees separated from you. And that's kind of the same with graph neural networks. Is if you represent something that is 7 steps away, then you'll just be representing the entire graph as a whole. So for example, what these visualizations are showing is if you look at a single layer graph neural network, we have the node of interest, and then we have the nodes that are connected to it. And this is only a handful, let's say 5. And then if you look 2 layers deep, so you're looking at the neighbors and those neighbors, you can see that it fills out a whole bunch more of the graph. But if you go 3 neighbors deep, we're basically covering everything in the graph. We only have a few nodes that we're actually missing here. And so we don't, it's nice to have this global view of the whole network, but that's not actually what we want. We want to be able to focus in and look at that node specifically. And so on this next slide, basically this is showing the overlap between 2 nodes, and it kind of illustrates the problem here. So if we have we have 2 different nodes that we're interested in, We have this node down here and this node up here. If we look at one hop, they only have a single node in common. If we look at 2 hops, they have a whole bunch of nodes in common. If we look at 3 hops, they cover almost the entire graph, and these are all shared nodes. So the messages that we're passing up, the aggregations, all of those steps up, eventually it's going to converge to virtually the same thing. So both of these nodes are going to have an embedding that is very, very close, because after all of this message passing and aggregation, we're taking into account all of these different nodes, and it's just covering the entire graph basically. So they might have some variation in terms of they don't cover the same nodes here, 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 over here, but it's going to be very minor because they have so much overlap that their embedding is going to be very close. And so this is actually a problem, because we don't want every single time that we do something it just to be representing the entire graph. We want that local piece that represents the neighbor. So like in the house example, you probably care about your neighbors and your neighborhood, but you don't care all the way about houses in France, for example. And so if we have over connectivity, we're going to show relationships that we actually don't care about. It's too far away, and we're just kind of taking a global look at the graph. So we have this problem where our receptive field is too big and we're covering too much of the graph. So then looking at how we overcome the smoothing problem while also having enough complexity of the network. So in general, the wisdom is that you don't actually want that many graph neural network layers themselves. You don't want to be going super deep through the network, and you kind of have to gauge that depending on the size of your graph and the interconnectedness and the complexity of what you're trying to do. So you don't always want to do 7 hops when 3 might be perfectly fine, or even 2. It just depends on the size and the interconnectedness. And so common wisdom in a lot of other spaces is just add more layers and you'll get a better representation. But in graph neural networks, that can cause some big trade-offs where you actually have too much connectivity, and then it ends up causing you problems. So then the question is, if we have this simple graph and we want complex representation of the features, but we don't want the total coverage of the graph, how do we do that? How do we get something that's significantly expressive but doesn't have too much interconnectivity? And so what we've done up to this point is just a single linear layer to encode the message, and we've done a single aggregation function to pull all of those together. But in actuality, if we want those deeper relationships and we're constrained to say three hops in the network before we start kind of over connecting everything, we can make these message functions and the aggregation functions more complex. So for example, we can put a box here, whereas before we might do a single linear layer, we could do a full neural network. So we could do 3 layers, we could do 5 layers, we could do whatever else, and it's making a much more complicated encoding of this initial message, and that can give us a deeper understanding of these features that we then pass to the aggregation function. And this aggregation function can also have a neural network at the end of it that does some deeper encoding as well. So instead of having a shallow GNN, we can have a deeper representation inside of our GNN. Another variant of this is that we don't put additional processing on the actual messages. We just have it on the input features and the final output layer. So for example, we have in this visualization, we have 3 graph neural network layers. So let's say we're doing 3 hops backward in the network. So we're looking at the neighbors. But then on the input features, we're more deeply encoding those. So when you're looking at the square footage, the rooms, the bathrooms, etc., you do some more layers just on the input, but then on the actual message passing and aggregation part, you just do the normal procedure. So you do a whole bunch more encoding at the beginning, but then after, when you're doing just the message passing, you do that same kind of standard single layer piece. And then at the end, you can also have additional post-processing layers. So you've gone through all of these message passing and aggregation steps. And then at the end, you have some vector, and then you just do a whole bunch of layers on top of that. But it doesn't make this GNN part actually more complicated. And so in practice, this has shown to work well, is just send it more complex input features to the GNN, and then do more complex output processing. And then you don't have to worry too much about the GNN layers, because these can potentially be a heavy operation if you're doing a whole bunch of connectivity and looking across a big graph. So then the other part that we can look at is the skip connections that I started mentioning earlier. So this can also help us with the over smoothing problem. So right, the way that we've discussed previously, you pass in the you pass things sequentially. So you have your neighbors, that goes into your neighbors, and then it goes to the neighbors, and then it goes to the target node. And that's great, but when you're that many layers removed from all of the other steps, eventually you've kind of aggregated and smoothed out a lot of the information. And so some way around this is to kind of directly pass the information forward. So then what you can do is you can say, take the information from the neighbors, and pass that all the way to just the neighbors, for example. And so you have a copy of that information that has been directly passed forward. And if you have a whole bunch of messages that you're passing, you're not smoothing away quite as much, because you're getting that initial representation again that you can still process on. So for example, here we have this information, and it goes through the graph neural network layer and goes to the next step, but it also just directly skips across it. So we have this sum plus the GNN layer that was already input. And so we can do skip connections, and that's been shown to have good impact. And that's the same thing with ResNets and computer vision, if you're familiar with those. Those use skip connections as well, and it's shown to work out well. So this is kind of showing more of the path of how all of this works. So for example, you have some input, you put it through the layer, and then that creates some output. But then on top of that, we're also passing this input directly over this layer. And then that's giving you the input features plus the transformation of those input features. And that's basically what a skip connection is doing. And this is a look at kind of the unraveled view. So by the end of it, you're seeing the information that passed from the first layer, and then the second layer, and then the third layer. But then you're also seeing the kind of second order messages being passed along and recombined. So that's kind of the gist of the skip connections, and there's various different flavors of that. So this is kind of just showing the mathematical formulation of it. So before, we were doing just the weight matrix times the specific neighboring node. And in this case, we can actually also combine it again with the input features. And so we're summing the linear transformation of this along with the original input feature. And so this is showing the skip connection on the right here. So another option that people have explored is, instead of skipping forward one layer ahead or something like that, you could just have everything skip all the way to the end. So you have this this input feature goes to the graph neural network layer. but then it also goes to the end. This one goes through another graph neural network, and then it goes straight to the end, for example. So then at the end, we have this sort of giga representation that shows the features from all of the different layers aggregated together in some way. So we can do it with all of the different techniques that we discussed before. So you can do concatenation, you can do max, mean, sum, etc. You can do LSTM, you can do all kinds of different things to combine all of the skip connections there. And I think that's it. I think that's the final slide. Right on time. Anyone? Any questions? Any slides to go back
Ryan,
to? Yeah.
so I'm just thinking at the idea of the skip connections. So like the intuition behind it, is it like what I'm imagining is something like, it's kind of regularizing the input instead of having the transformed input. Let's say if you look at the example on the left through F1, you're also getting the the untransformed input above it, like the skip one. So it's kind of like fx plus x is kind of doing some kind of regularization to make it more robust. Is it that kind of idea?
Yeah. It's trying to pass the information forward so that you don't have just a super deeply transformed output eventually. So eventually, if we say let's pass this single input through 50 layers, for example, then it has to go through all of that to pass the gradient backwards. And so this additional skip connection kind of gives us a fast forward back to the beginning of the network, so it can learn deeper back into the earlier layers. One of the motivations behind the skip connections is to give the gradient, the learning signal, the ability to reach further in the network. Because if you do it a network that's very deep, it's hard for that gradient to pass all the way up a chain of 50 layers, for example.
Right, because of the vanishing gradient problem.
Yeah.
Okay, got it. Okay, thanks.
Just want to mention that at some point when convolutional neural network just started, I remember being on a talk where the presenter said that they tried different kind of numbers of layers and they stopped getting anything new after 6 layers. So they don't think that you should use any more than 6 layers, because yes, it is smoothing and such and such. And then people come up with more complicated structures.
Yeah.
I actually have seen a paper, Maya, as you said that, I was getting into text with CNNs, and I saw there is a paper, you can Google it, VDCNN, very deep CNN, and that network has about 29 layers actually. So I really don't know what's the, like, was it successful? Was it a good paper or not? But I think gone through it like 2-3 years ago.
Yeah, there's plenty of different research on the depth of networks and what exactly that means for performance. I think it largely depends on your data set too. So people have been lately doing these extremely large data sets, and it's been shown that more layers can give you a deeper representation of this and then be useful. But I think in a lot of people's cases, you don't need so many layers to actually represent what you want. But yeah, I think that's just an open area of study.
Yeah, agreed.
The question about the convolution, the operation is not really a convolution like in CNN, right? It's a little different.
Yeah, yeah. I mean, I don't know exactly how I would liken the two. I don't know the formal definition of convolution, so I can't argue either way, but I can definitely see the, where was it with the CNNs at the beginning? That you can definitely represent this kind of CNN in the same form in the graph neural network form. But when I think of the convolutions, normally you're kind of doing this sliding window. And I guess in a certain sense, you're doing the same thing with the GNNs, but across the nodes that you're interacting with. But I don't know about the formal definition of that, so I can't really liken the two.
Okay, thanks.
All right. Well, we are 7 minutes over. We actually did pretty good in terms of time. So thanks everyone for coming. We will wrap it up here. And then what we typically do after this is we have sort of open office hours. So if anyone has any questions, if you have anything you're working on, if you just need help with anything, want to talk about career stuff or whatever, always happy to do that. But for anyone who just wanted to talk, feel free to hop off now. And then we can swap over to this other session.